just have a few last minute loose ends to tie up. So we'll write those in our comp book now, and then we have a short lab to do. So it will not be one we need to write up though. So because we have enough to do this week. Yeah, if I had one. All right. The last thing I want to talk about is this L. This L is what we called angular momentum. Abby, P was our old momentum, and L is when you're rotating. So let's just, we talked about it with the skater and with the cat, but now we're going to actually just do one with numbers. So let me make a child's toy. Tell me if you think they'd buy this. We can send you all to Europe free if we sell this toy. All right, so say we're spinning this, and watch what happens. I'm not going to change the force that I'm spinning it with. I'm just going to change the radius. Wow. It went much faster. You think it'll sell?
I think as a little kid would just take it and
that really
spin.
I think a little kid would hurt someone.
I don't know.
All right, somebody take your own Europe trip. All right.
My mom always said, don't spin things over your head because you'll hit somebody.
Oh, I hope she doesn't view our class. All right, we're going to draw the toy. So draw the toy in your comp book. It has sort of a cylinder with a toy, something. We'll make it a fly or a bee, or what was something a kid like to spin? An airplane. We'll make it an airplane. So we made this toy to fund our trip to Europe. So as it goes around, the radius is known. The radius is 34 centimeters, but you know we never use centimeters. And I noticed on your pinks that I just handed back, a lot of people were saying 34 centimeters is the same as 0.34 centimeters. Remember, you only move the decimal twice to go to meters. If you're going from grams to kilograms, the word kilo should tell you that it's 1,000. So this is a centi. There's 100 cents in a dollar. You just move it twice. So are you taping yet?
Yep.
Okay. 0.34 meters is what we really use when we actually put it in the equation. All right, we know the velocity initially, and it's write that as 3.2 meters per second. And I'm going to pull on the string, and the radius is going to go down to 12 centimeters. So we're going to change radius to 0.12 meters, and I'm going to ask what's the final velocity of the airplane, the toy. Find V final. So we'll pull out our equation for L, MVR before, equals MVR after. And we don't care about mass because there's mass appears once on each side, and we have the joy of crossing it out. So put in the numbers now, before, the velocity before, the radius after, and solve for the final velocity. Go ahead and tap away and tell me what you get. Are you setting it up correctly? 3.2 times 0.34 equals unknown V times the new radius. Not a very difficult one to tap out. Nothing's even squared or square rooted. So, what are you getting?
I got 9.
9?
Yeah.
9.0?
Yes.
9.0 meters per second. Is that faster? We started with 3.2. It is. So it looked like it was going a lot faster when I pulled on the string. So, all right. Another concept I just want to end, just sort of tie up. It was one I left over. And I don't know if we wrote this down. It came out in the middle of a problem, but let's write it down.
Is it
And-
the 7/10 thing?
Pardon?
No.
No. 7/10 thing we can forget about. That was just for that moment. All right, another word about conservation of momentum. Would you write this sentence and see if you can fill in the blank? You probably can, but I just want a clear note in your books. Any object that launches another object experiences a blank velocity. Don't say it out loud, just fill it in if you know. We've done problems with this, like the cannon and the gun. See if you remember the name of that velocity. Experienced by the object actually doing the launching. So I'll draw one. The cannon. Here's an example. So there's an object launching another object. So it experiences a blank velocity. What's the name of that velocity that the actual cannon experiences? So the cannonball is going to go that way, and the cannon actually moves that way. What's that called? Anyone? Recoil. Very good. So recoil velocity is that opposite velocity that the launcher experiences, the thing that does the launching. So when you shoot a gun and it hits you in the shoulder, that's recoil velocity that we're talking about. Let's look at this special one recoil, and I'll explain lab to you. This time, lots of times in physics class, the teacher will ask the students to explain why a rocket will lift off. So it's a type of recoil, actually. So here's your rocket, draw a rocket, and inside draw the molecules that are going to go under combustion of some sort. And we do, this is not circular or anything, so it's just regular conservation of momentum. mv before equals mv after. So draw a little rocket and some molecules about ready to combust. So before, there's no motion at all. So we have a lot of mass, but we don't have any velocity before. And after, so actually before, the mass is created by two things, the rocket plus the molecules. And the velocity is created by two things together, the velocity of the rocket and the molecules combined. But before, the rocket isn't moving at all, so this is all zero on before, the before picture. But after, the little molecules explode out the back after the combustion. So now these two are separated. So we have mass of the rocket, velocity of the rocket, and then separate mass of the molecules, velocity of the molecules. Write that down and I will explain to you and see if you can understand why the rocket is moving. Because I'd say 5 out of 10 physics students, even after this lesson, will give me the wrong reason. So see if you can figure this one out with me. All right, are you okay that before the explosion, the rocket and the molecules are together? One is inside the other, and they aren't moving at all. Are you okay with after it? The molecules come out, and now they are calculated separately from the rocket. All right, so let's talk about what is the mass of the rocket. Is that a pretty big number or a small number? Mass of the rocket.
Big.
All right, so we'll just say big. We're not going to be too specific on this one. The velocity of the rocket is what we're talking about. So let's just call it VR. We're interested in why it's going to move. So we'll call it VR. Then we have the mass of the molecules. As the molecules take up very much mass.
No.
Compared to the rocket, I mean, there might be some sort of box in there that has some size, but it's going to be small. So the fuel compared to the rocket is small in size. what about the velocity of the molecules? The velocity of the molecules. When these molecules come out, what about their velocity?
Is it really fast?
It is like
lightning.
it's like huge, and you're going to add them all together. So this is like huge, 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 huge. I only write 2 of them. Huge, huge. All right, so remember, this has to equal 0. So if we move this small number times huge, huge, it comes over here and it becomes negative, but it's going to have to equal this number. So it'll be negative because the rocket will go in the opposite direction as the molecules did. So don't worry about the sign. But for this number to be big, but not great, it's a big number, it's the mass of the rocket, but it's going to have to equal this number over here. And this is a small times a huge, huge, huge number. So a big times, what do we need here?
Another big number?
Another pretty big number. We need a pretty big number here to equal this small times the huge, huge number. So because of conservation of momentum, the rocket must have a velocity. And it's pretty big, a pretty big velocity. So this is big as well. And the whole reason it lifts off, most students will tell me, even after this discussion, will say the molecules come out of the rocket and push on the ground and send the rocket up. But that's not why. It's conservation of momentum is why. Because of this equation, they have to be equal. So the only way they'll be equal is if the rocket takes off. So it's really cool when you think about it, the implications of conservation of momentum. Questions on why the rocket takes off? Can you explain that in your own words come Wednesday? Yeah.
I just have a question. Isn't that why they thought that JFK was assassinated by 2 people?
Because conservation of momentum?
Well, because of like recoil.
Oh, really?
Because like he was shot in the back of his head
And-
and it came out the front
Right.
and his head like went back.
Yeah, I did see
That's why
that.
His brains like.
I did see that. I know, there's so many different theories about that. With all the physics we know, you'd think we could figure it out.
Well, I mean,
Because it's all on camera.
I know, but there's no proof that there are 2 people. It's
Yeah, just a theory. Yeah. Yeah, his head did go back, so how do you figure he gets shot from there?
Maybe his brains blew out.
I know,
And
it was
his,
so
like, his
awful.
wife's face too.
I know, it was an awful thing.
You sounded almost happy.
All right. I think that's all for us. Annabella, we're going to do a lab now, and maybe we will tape of somebody doing it, and then you can see what happened. So that's all for the instruction part. So over and out.